So, good afternoon and welcome back after lunch for the second part of the workshop today. And we will start with terms and definitions. I show you a small picture of the equipment. Thereafter, we will have a look into thermal reactions in clays in general. After that, we have to deal with factors that influence the outcome of our measurements, because in thermal analysis, you have a huge influence of the experimental parameters that you choose on the result of the analysis. So it's not like an X-ray diffraction analysis that you can calculate a pattern based on the structure and size and strain of the minerals that you assume. Here you have to know which parameters you apply, and when you want to compare your data with data from literature, you really have to compare also the measurement conditions. Yeah. Those experimental parameters then result in a parameter list or a table that you always should publish together with your data, or that you should take as a list to find the information in publications. And then I'll show you thermal reactions of clay minerals. So as far as we were able to separate nearly pure clay minerals from bulk clays. And I will show you a few slides of related to quantitative analysis by the use of thermal analysis. And then at the end, I'll show you how to read a curve with a few examples. Okay, there are basically two methods of thermal analysis, which is isothermal analysis or dynamic thermal analysis. The isothermal analysis is performed under constant temperature. You all might know determination of the water content or the determination of the loss on ignition. So those are the most common isothermic or static thermal analysis methods. And in contrast, we have dynamic thermal analysis, where you apply a defined temperature time program. Yeah, you can heat your sample with a defined heating rate, then you can keep your sample at a certain temperature, heat it again, cool it down. This depends on the question you want to solve by thermal analysis. Yeah, you're free to apply any temperature time program as long as your equipment allows the program. And then you observe changes in different physical or chemical parameters. Most easiest thing again is observation of changes in mass, but also we can observe changes in the temperature of our sample with a reference sample, and then calculate reaction energy. You can also monitor the dimension of your sample, so there are various applications or measurements that you can do. And most modern equipments, like you see here in this picture, are so-called simultaneous thermal analysis devices, because they allow you to monitor at least two different parameters. Most of the time, this will be the mass change and change in the temperature of the sample, indicating if an endothermal or exothermal reaction is taking place. But there are other combinations, and this picture shows you a combination of TG. So this is the oven, there's the balance underneath, and then this device is coupled to a mass spectrometer for the analysis of evolved gases. You also can couple your device with gas chromatography, infrared spectroscopy, any method that allows you to analyze evolved gases. So again, there are several options. And those are the curves that we obtained by our device, and you will recognize this type of curves in several slides during the talk. On top of the sample that we measured here is a kaolin with a very high kaolinite content. On top you see a so-called DSC curve, differential scanning calorimetry curve, and During this measurement, you measure the temperature in your sample and the temperature in a reference sample that shows no thermal reaction in the temperature range that you apply for thermal analysis. And then if your sample has, for a certain period of time, a slightly lower temperature, you measure a voltage, and then you see a peak. And we always plot endothermal peaks downwards and exothermal peaks upwards, and this is also indicated by an arrow. But if you have a look into literature published by chemists, very often the curves are displayed the other way around. So this might be sometimes confusing, but that's why it's very important that you always indicate in which direction you plot the exothermal peaks. The second curve, if you have another device called differential thermal analysis, the curve would look totally the same. You just cannot then calibrate the device to determine reaction energies. So these devices allow you to calibrate the measurement, and then from the area of a peak you can derive energies, which is not possible if you have a DTA device. The second curve you see here is so-called thermogravimetric curve, TG, and there you see mass changes. Most of the time it will be a mass loss, but I will show you an example where you also can observe a mass gain in minerals that you find in clays. And at the bottom you see an example of a curve from the mass spectrometer. This is the mass spectrometer curve of mass 18, which is characteristic for evolved water. And here you see at the top in the DSC curve, you have an endothermal reaction with a strong mass loss, and the mass loss is caused by water evaporation. Yeah, and this indicates that the dehydroxylation of the kaolinite takes place. So the mass spectrometer curve, or the mass spectrometer curves, always support your interpretation of the DSC and TG curves, because I will show you an example where you see that in a natural clay or in a soil, very often thermal effects superimpose. And then it's really difficult to decide whether it's an endothermal or exothermal reaction taking place and what is evolved during this reaction. And with the help of the mass spectrometer, you get a better idea of what's going on in your sample. You have to be careful. There also a curve exists which is called DTG, and this is the first derivative of the TG curve. So in the first case, we measure a difference, and in the second case, it's the derivative curve. And what you should remember after this lecture is that any clay mineral is characterized by 4 thermal reactions. Those 4 reactions are the dehydration, the dehydroxylation, the decomposition, and recrystallization at high temperature phases. You see here a DSC curve of a montmorillonite. Montmorillonite is the most common dielectric-smectite, most common swallowable clay mineral. And at the bottom you see a DSC curve of kaolinite. And here you already see the differences between swallowable clay minerals and non-swallowable clay minerals. In the case of the smectite, you see a strong endothermal peak for the dehydration, because smectites take up quite a lot of water, even at ambient conditions. But in the case of kaolinite, which is a non-swallowable clay mineral, there's only some water at the outer surface absorbed, and so you have a very weak endothermal reaction for the dehydration. For the dehydroxylation, you see the intensity for the montmorillonite. Again, dehydroxylation is an endothermal reaction. Intensity is lower compared to kaolinite. And this is because in any 2-to-1 layer silicate, during the dehydroxylation, 1 water molecule evolves. In the case of the 1-to-1 layer silicates, 2 water molecules evolve during the dehydroxylation. So then of course you have a stronger peak for the dehydroxylation. And as you can see, for both minerals, very often you don't see the endothermal reaction of the decomposition at higher temperatures. And in the case of the smectite, the exothermal reaction of recrystallization of one high temperature phase could be very weak, in contrast to the recrystallization of the first high temperature phase of kaolinite. And this is because kaolinite has a very defined stoichiometrical composition, no substitution. And therefore we have very defined high temperature phases that crystallize. In the case of smectites or any 2-to-1 layer silicate, we have a lot of substitutions, or very different high temperature phases can form, and they form one after each other, so we have a broad peak, or sometimes you cannot recognize the recrystallization of the high temperature phases. Okay, so please remember, any clay mineral is characterized by 4 characteristic thermal reactions. And those thermal reactions are interesting for several applications. So at room temperature and low temperatures, hydration and dehydration behavior is interesting. For instance, for the use of clays in medical applications or cosmetics, and also for the use of clays in environmental protection, for instance, in radioactive waste deposits. The dehydroxylation behavior at intermediate temperatures is interesting, for instance, for the use of calcined clays in so-called green concrete applications, or as precursors for geopolymers, or as pozzolanic supplementous cementitious materials. And at the bottom you see also a vermiculite that was heated up to the dehydroxylation temperature, and this material can be used either as isolation material, or it also can be used in soil science if you want to perform plant growing experiments and you want to study microorganisms. You need a soil that has no initial microorganism inside, yeah, and then you can use this heated vermiculite as a soil replacement for your soil plant growing experiments. And the reactions at high temperatures are interesting for the production of ceramics, or production of cement, or production of bricks. Yeah, so there are many other applications, but so you get an idea that information from thermal analysis are very helpful for various applications and questions you want to solve in your research. And this is how a DSC curve of a clay could look like. So this is a DSC curve of an Opalinos clay, and I like this for teaching because here you see all thermal reactions that you can expect to happen in a clay. Yeah? And then you also see that it's sometimes really difficult to decide whether it's an endothermal or exothermal reaction. So this Opalinos clay was heated in streaming air, synthetic air. You see at low temperatures dehydration takes place. You see a very intense endothermal reaction. But then this dehydration is followed by the oxidation of organic matter and the oxidation of pyrite, iron sulfide. So, and here you see, if you don't have any experience, you don't know if those are 2 endothermal reactions that are superimposing, or if you see 3 exothermal reactions that are superimposing. So you just have to believe me, and that I tell you, okay, these are 3 exothermal oxidation reactions. Okay, and these reactions are followed by the dehydroxylation of the clay minerals. What you can't see here is the transition of quartz, because there's not so much quartz in this Opalinos clay sample. But if there is sufficient quartz, you also would see a small endothermic peak for the transition of alpha into beta quartz. And then here you see the decomposition of carbonates, that is also an endothermal reaction, and then followed by decomposition of all the phases together, and the crystallization of the first high temperature phase. And again, here you see the help of the gas analysis. I told you those two exothermal peaks are related to the oxidation of pyrite. Yeah, so you just have to believe me or literature that tells you this interpretation. But here you see the mass spectrometer curve of evolved SO2. Yeah, and right at at the same peak temperature, you see that SO2 is evolved from the sample. So, and this supports the interpretation that there the oxidation of the iron sulfide takes place. And what you also can see in this curve here, at high temperatures, you see again that SO2 is evolved. And this shows you that thermal analysis, especially if linked to mass spectrometer or FTIR or whatever to analyze the evolved gases, is very sensitive to decomposition reactions during heating of your sample. And this SO2 release at high temperature could have two sources. Either in your sample was also a sulfate at low concentration, or if you have a clay where you have also some calcium from carbonate, like in this sample, then after the oxidation of the pyrite, some SO2 can be reabsorbed in the sample, forming anhydride, and then it's released at high temperatures. And now we talk about all the experimental parameters that influence the results. What we want to learn from thermal analysis is information about the composition of our sample. We also can get information on particle size or crystallite size if we think about samples that contain, for instance, natural carbonates that are dissolved and precipitated again, then you most of the time observe a change in the crystallinity that you will see by a shift of the decomposition peak. We also want to get information on the order or disorder of clay minerals or on the structure. But to get these information out of our measurements, we really have to be careful with the applied parameters like heating rate, the atmosphere, even the amount of material that we put in the crucible during the analysis influences the result. And this I will show you with the next slides. Influence of the sample weight in your crucible. And this very often, if you compare your data with data found in literature, very often the sample weight is not reported, or people don't take care that they always apply the same amount of sample when they want to compare their data. Yeah, if they have like 10 samples they study, sometimes they apply 20 milligram, sometimes 30 or 40, and then it's really hard to compare the curves that you measured. Here again you see the kaolin with a high kaolinite content, more than 80%. And here you see we varied the sample weight between 3 and 104 milligram. This again is the mass spectrometer curve of evolved water. And what you see, of course, with increasing sample weight, the intensity of the peak increases, but also the peak position shifts to higher temperatures. And this was reported by Smickards-Kloss, and this dependency, this logarithmic dependency is called Probenmengenabhängigkeitskurve. This is a German word. There is no English translation. It means dependency on the sample weight. And the English abbreviation is derived from the German word. So that's why these curves are PA curves. Yes?
Whenever I was doing TGA early on, because I'm not an expert in it, I always thought this was a kinetic response. So I thought about just holding my temperature or my sample for a longer period at that temperature. Does that eliminate this effect?
So I will repeat the question for the people that are remote. The question was if this is a kinetic effect and if this can be overcome by holding the sample at a temperature, one temperature for a longer time. This would even create a broader peak with low intensity, and then it could happen that you don't see any peak at all. If you keep it too long at the same temperature, because then, you separate the reaction in very small increments, and then you will lose intensity and broaden the peak. And here the influence of the weight is the onset temperature actually would be the same. Yeah, but very often, as we have these superimposing reactions or effects, we have to rely on peak positions. And then, of course, it's a kinetic effect and also an effect of the atmosphere that is created within the sample, because if there's a gas involved, it has to diffuse out of the sample, and therefore, we get this shift in the peak position. But you should be careful if you lower the heating rate too much or perform isothermal analysis, because then sometimes you don't see a peak at all. So at the end of my talk, I give you some recommendations on books to read, and Smickalsklaus published a whole book for various clay minerals and other minerals that you find in clays on the dependency of the peak position on the sample weight. And what you can see here, if you always work with a low sample weight, and then one time you use 10 milligram, the other measurement you use 15 or 20 milligram, you see you have a large difference in the peak position, because it's a logarithmic dependency. If you apply 100 milligram, it doesn't matter if you apply 102 or 98 milligram. So then the deviation in the peak temperature is much lower. But you can use this effect the other way around. If you're thinking about studying a profile, soil profile, sediment profile, or whatever, and you have only one phase, or you can separate the decomposition peaks of one phase from the other phases, and you see a shift in the peak temperature. If you apply 100 milligram of your mixed sample and you observe a shift in the peak temperature, this indicates a change in the amount of the single phase in the clay sample or in the soil sample. So you could use this effect both way around, but you have to think about of the weight you use for your analysis when you want to compare samples, different samples. Okay, then of course there is an influence of the atmosphere. So if you heat calcium carbonate in vacuum, of course, then the evolved CO2 is removed very fast from the sample, and so the composition takes place at lower temperatures compared to heating calcium carbonate, for instance, in a CO2 atmosphere. Then you have to apply higher temperature. And the same is valid for instance, the dehydroxylation or the dehydration of a clay mineral in an atmosphere that contains water. The curves you see here are DTG curves of the dehydroxylation of montmorillonite. The upper measurement was performed in synthetic air. There's no water in this synthetic gas. You see here this montmorillonite is characterized by two dehydroxylation peaks. I will give you the explanation for this double peak later. But you see, if we add water vapor into the atmosphere, then the dehydroxylation shifts to higher temperatures. And this you also have to consider when you perform only TG measurements, and then there you have the opportunity to use very large crucibles. Normally you can use like 100 milligram during a thermal analysis, but for TG measurements there are also crucibles available that can hold up to 5 grams of material. And this sometimes might be helpful if you have very heterogeneous materials, or if you want to study aggregates or compacted samples and you don't want to destroy the sample before you perform thermal analysis. Yeah, then you might apply this, or you might use these large crucibles, but then you have to think about an atmosphere that can form within the sample. Yeah, because if a gas is evolved, it has to diffuse out of the sample, and as long as it stays in the sample, yeah, you can create an atmosphere that will hinder further development of gases. But sometimes, yeah, if you think about ceramic production or any technical applications, yeah, where you heat a clay or a soil, these effects also can happen. Then the effect of heating rate. This is siderite, not a clay mineral, so iron carbonate. It is well known that the thermal decomposition of siderite occurs in 3 steps. So first we have the decomposition, endothermic reaction, CO2 is evolved, and afterwards the iron oxide is oxidized in 2 steps. So this is well known, but on the left side, we performed the thermal analysis with a heating rate of 5 Kelvin per minute, which is quite common. So most common heating rate would be 10 Kelvin per minute, but very often 5 Kelvin or 20 Kelvin per minute are applied. And when you have a look at the TG curve, you see only a mass loss. Yeah, you see a strong mass loss. This could be related to the decomposition, but you don't see any mass gain from the oxidation. And even worse, if you have a look at the DTA curve, it shows only one exothermal peak, but we know that any decomposition is endothermic reaction. Yeah, so those reactions are superimposing and you don't see them in the DTA curve. If you perform a measurement with a heating rate of 50 Kelvin per minute, again, TG curve, and now you see the mass loss due to the decomposition of the carbonate, and then you see a mass gain. Actually, it's a 2-step mass gain, the first one here and the second one here, due to the oxidation of the iron oxide. And in the DTA curve, you now see the endothermal decomposition followed by 2 exothermal oxidations. Yeah. So if you already have an expectation of the thermal effects that you should observe, and if you don't see them, play around with the heating rate, and then sometimes, or very often, then you will be able to see all the effects that you expect. And this is important to keep in mind because sometimes you vary the heating rate to separate superimposing thermal reactions. Yeah, and so sometimes you have to perform not only one measurement, 2. Sometimes you have to play around a little bit to find the proper measurement conditions to retrieve all the information from your sample. Sample storage, sample preparation also has an influence on the outcome of your thermal analysis. We heard already in the morning during the talk of Bruno Lanson about the hydration of smectides and how this influences results of X-ray diffraction analysis, and we also see that we get this information from thermal analysis. Water content. You might think, well, this is an intrinsic parameter that is characteristic for my clay. Yeah, but on the left side, you see 3 different bentonite samples. Calcigel is a calcium bentonite, wall clay is a sodium bentonite. And this Spanish bentonite was pre-treated, that's why water content is very low, but it's also calcium magnesium bentonite. And we determined the water content many years ago, but anyway. Try better, water content, we determined a certain value, but then afterwards we had some thunderstorm, lots of rain, and then we measured a different water content. Yeah, because water content is always an equilibrium between the clay or the soil and ambient conditions, relative humidity and temperature. So that's why water content is not an intrinsic parameter. And if you need the water content to refer any other measurements like cation exchange capacity or whatever on the dry weight, yeah, you always have to determine the water content at the same time when you start all the other measurements. Yeah, if you have to recalculate something related to the dry weight of the sample. Or you have to make sure that you store your sample always under the same conditions, constant relative humidity, but also constant temperature. Yeah, so because even if you have a constant relative humidity and the temperature in your lab is changing quite a lot, you will change the water content in your sample. Yeah, so this you also have to keep in mind, especially when you work with swellable clays and clay minerals. Yeah, because there you have the highest influence from relative humidity and temperature on the water content. Yeah, this is what we learned from Bruno, and this is the explanation of why the same smectite with different interlayer cations has different basal reflections. Yeah, because here you see they are in a different hydration state. Yeah. So this is one montmorillonite with different interlayer cations, and you see the dehydration behavior takes place in several steps. So this sample probably was stored at higher relative humidity, so no information are provided for this figure, but you see yeah, a huge difference which is related to the hydration properties of the interlayer cation, but it's the same on mononite. And the interlayer cation also influences the dehydroxylation temperature. So if you want to study the difference in the dehydroxylation behavior of different smectites, for instance, you have to make sure that you first prepare homoionic saturated samples and use the same interlayer cation. Otherwise, if you see a shift in the peak temperature, it might not be related to the octator structure, it only might be related to the interlayer cation. And with these explanations on the experimental conditions, you see that you always should yeah, report this information, and you also should have a look when comparing your data with literature data if they gave all the details how they performed the measurements. Coming back to the water content, depending on the community where you work, like soil science, mineralogy, or civil engineering, geotechnical engineering, there are different ways to calculate the water content. So I think for soil scientists and clay mineralogists, the more common way to calculate the water content is to relate the mass of water to the initial weight of the sample. Yeah, we call it the wet sample because it still contains the water. In civil engineering, geotechnical engineering, the water content is calculated related to the dry mass of the sample. Yeah, after you determine the mass loss by heating. So we made several attempts to find a wording to distinguish between the two calculation methods because when you're working in a large interdisciplinary project yeah, with soil scientists and engineers, sometimes everybody is talking about the water content, but people mean different things. And for the moment we go with moisture and water content to make it clear how the water content was calculated. And to get an idea about the meaning of both calculations, if you think about a sample that contains 50% of a solid and 50% of water, yeah, so the moisture would be 50%, yeah, because half of the sample is water. But in the case of the geotechnical water content, the water content would be 100. Yeah, so with this figure you always can imagine the difference between those two calculations. And so the moisture can only vary between 0 and 1. 1 would be pure water. But for the geotechnical water content, you can get values that are much higher than 200 or 300%, yeah, because it's just a calculation. But you don't need all the data from the measurement. Yeah? If you know how it was calculated, you can transform moisture into water content and water content into moisture. And normally, if we would have more time, I would ask you to do the calculation, but now I show you how to derive the transformation equations. So here you see those values can be transformed into each other. So don't worry, just ask how your colleague calculated the water content. And if you need the other value, just transform it. And now we are coming to the question why we have to apply 200 degrees Celsius to determine the water content of swallowable clay minerals and swallowable clays. You might think, okay, there are norms, they tell us how to determine the water content of a soil, and it says, okay, put it in an oven and apply 105 or 110 degrees Celsius, and then you can, the mass loss is equal to the water content. But this is what we always forget. Already Hoffman and Bilke in 1936 stated that in montmorillonitic clays there could be still found some water after heating at 110 degrees Celsius. And especially if you have a divalent interlayer cation like calcium or magnesium, they have high hydration energies. If you determine the water content by heating at 105 degrees Celsius and then compare it to the water content determined at 200 degrees Celsius or determined by simultaneous thermal analysis, because by simultaneous thermal analysis you really see the end of the dehydration. Yeah, then you see up to 4 to 5 water molecules per interlayer cation remain in the sample. So if you determine the water content of a bentonite at 105 degrees Celsius, you measure a number, but that's not the water content. Yeah. And this is important if you want to balance anything or calculate dry density, saturation, whatever is interesting for the use of bentonites, for instance, in radioactive waste deposits in the engineered burial system. Yeah. Okay. And it's an issue about the water vapor or the partial pressure of the water vapor. It's not only about the temperature. So we did some theoretical calculations I cannot show you today, but I can give you an explanation from the measurements. Here you see the TG curve of the dehydration of a sodium exchange montmorillonite that was stored at 53% relative humidity and 25 degrees Celsius. You see the mass loss, and here in blue you see the mass spectrometer curve of the evolved water. Yeah, and you see that only at 250 degrees Celsius roughly the reaction really finished. Yeah. If you apply a very low partial pressure of water vapor and you can apply a very low heating rate, then even 100 degrees Celsius would be sufficient. Yeah, this would equal isothermal measurement in a conventional furnace, but then you have to make sure that you either flush your furnace constantly with a dry gas to remove the evolved water, or you apply vacuum. And then it's also possible to determine the water content at room temperature. But you have to make sure that you lower the partial pressure of the water vapor sufficiently. And commonly, when you determine the water content in an oven in your lab, you neither apply vacuum nor apply streaming dry gas. Yeah? And then you always have remaining water molecules in the oven from the atmosphere, and that's why 105 or 110 degrees Celsius are not sufficient to determine the water content of swallowable clays. This slide will show you that the hydration of clay minerals is not always related to the surface, or it's not related to the surface that you measure by nitrogen adsorption or argon adsorption. On the left side, you see the mass spectrometer curves of evolved water again, and we are now interested in the low temperature range. On top, pyrophyllite, non-swallowable 2-to-1 layer silicate, dioptrital, no substitutions. In the middle, illite, also a dioptrital illite, and at the bottom, sodium saturated montmorillonite. First thing that you see, pyrophyllite is non-swallowable. Particle size is around 2 micrometer or even slightly larger. You hardly see any dehydration because there's hardly any surface that can where water can absorb. In the case of illite, it's also a non-swallowable clay mineral, but here you see, relatively strong dehydration peak, and so we were wondering why we see a strong dehydration for this sample. First of all, peak temperature is below 100 degrees Celsius, and then if you have a look at the ratio between the dehydration peak and the dehydroxylation peak, the dehydration peak is not that strong. But this illite had a very small particle size, therefore more surface area, and so therefore even it's a non-swallowable clay mineral, water could absorb at the outer surfaces. And in the case of the montmorillonite, you see peak temperature is much higher than 100 degrees Celsius for the dehydration. And you see the intensity ratio, when you compare the dehydration peak with the area under the dehydroxylation peak, then you see we have a very strong dehydration. Quite a lot of water is evolved during the dehydration. And I already explained the illite was very, very fine-grained, very small particle size, and so those two surface areas were measured by nitrogen adsorption, and they correlate with the adsorption of water vapor, because in pyrophyllite and in illite you only have the water adsorption at the outer surfaces. The water cannot penetrate the interlayer. In the case of the montmorillonite, you see the surface area measured by nitrogen or argon adsorption is smaller than the surface area for the illite. But in the case of swallowable clay minerals, the hydration takes place in the interlayer. First, due to the hydration of the interlayer cation, that is then followed by osmotic hydration, filling up the interlayer by forming water-water networks. So be careful, sometimes water vapor adsorption is suggested to measure the surface area also of smectites. This was applied in the past because by chance, if you have an intermediate layer charge and you store the smectite or the bentonite at 75% relative humidity and you have sodium in the interlayer, if you fulfill all these criteria, then just by chance, the water that is needed for the hydration equals a monolayer of water molecules around the outer surfaces and the interlayer. But if you think about the definition of smectites, where you have a layer charge between 0.2 and 0.6, and you also can have different interlayer cations, then you get again numbers, but then the amount of adsorbed water at 75% relative humidity do not correlate at all with the surface area of the smectite. You easily can calculate the surface area of a smectite from, if you know the lateral dimension of your particles, you know the thickness of the layer, and then you can calculate the specific surface area. And now I'll just show you a few examples of clay minerals, how you can identify them from thermal analysis. And we will start not with clay minerals, but with gibbsite and prussite to show you the influence of the octahedral element. You see in the case of gibbsite, the dehydroxylation temperature is much lower than the dehydroxylation temperature of prussite. Normally, we apply 100 milligram as a standard weight for our measurement, but in the case of gypsite and prussite, so much water is involved during the dehydroxylation, the device cannot measure it anymore. That's why we reduced the sample weight to 10 milligram, and then we can extrapolate a dehydroxylation temperature that we would expect with a higher sample weight. Now we come to the thermal reactions of kaolinite or diatrital one-to-one layer silicates, also polytypes of kaolinite. You already saw this curve: dehydration, dehydroxylation, decomposition, and recrystallization. And if you calculate the stoichiometric mass loss during the dehydroxylation, you get a value of 13.94. Please remember yourself, roughly 14%, because this is what we need later during the exercise. Okay, and this high mass loss is explained by this evolved two water molecules compared to the one water molecule that is released during the dehydroxylation of 2-to-1 layer silicates. Dikite, it's a polytype of kaolinite, same stoichiometric composition, different structure. And here you see that dikite dehydroxylates at much higher temperatures than kaolinite. 2-to-1 layer silicates. You know the definition. We have the uncharged pyrophyllite and talc, and then with increasing layer charge, we have smectites, vermiculite, illite, and then the micas. Again, 4 thermal reactions: dehydration, dehydroxylation, decomposition, and recrystallization. And the intensity of the dehydration then depends on substitutions, yeah, and not substitution, swellability. In the case of pyrophyllite and talc, no swellability. We have a very weak dehydration peak, or we see a very weak dehydration peak. The same for illite and micas. Non-swellable clay minerals in the case of smectites and vermiculite that are swellable clay minerals, there we see a very strong peak during the dehydration. Dehydroxylation, this is a short form to write. You see 2 hydroxide groups produce 1 water molecule and a remaining oxygen in the structure. And you should remember stoichiometric mass loss between 4.75 and 4.9, so yeah, stick with 4.85 roughly. And for the crystallization of high temperature phases, in the case of a triactital like talc, ensanthid would form with segregation of silica. In the case of pyrophyllite, mullite will form, but for any other minerals, smectites, vermiculite, illites, we get different high temperature phases, and therefore broad peak, or we hardly can see a peak for the recrystallization of the high temperature phases. This is how a DC curve of a pyrophyllite could look like. You don't see anything, right? And this is the effect of particle size or compaction, yeah, creating an atmosphere within the sample, and then the dehydroxylation takes place over a huge temperature range. And with the help of the mass spectrometer curve of the evolved water, now we see the dehydroxylation as expected. But you see here, it starts below 600 degrees Celsius and doesn't end up to 900 or even higher temperature. So yeah, you need this information on the particle size, or you also have to think about if you're studying an aggregate, compacted sample, whatever. Yeah, this can influence the thermal reaction. Talc compared to pyrophyllite, talc is a triactital mineral, magnesium in or at octator positions, dehydroxylation temperature is much higher compared to pyrophthalate, which is a dioctator 2-to-1 layer silicate with aluminum at the octator sheet. Montmorillonites, I explained it several times. Here you now see the full stoichiometric equation for the dehydroxylation. Okay, I already explained the influence on the interlayer coloring on the dehydroxylation temperature. We also saw examples for the influence of the occupation of the octator sheet. The bond between magnesium and the hydroxide groups is much stronger. That's why triaxial 2-to-1 layers, or in general, triaxial clay minerals dehydroxylate at much higher temperatures compared to the dioctator ones. And if you have a high iron content in the octator sheet, dehydroxylation temperature is even lower. And then we also have an influence of the octahedral structure in dioctator 2-to-1 layer silicates, because in the dioctator minerals only 2 out of 3 positions are occupied, and they have a different bond to the hydroxide groups. I will show you later. First, the influence of iron. This is a non-tronite, and here you see the dehydroxylation temperature is much lower than we saw for the montmorillonite on the earlier slides. Aluminum will then increase the dehydroxylation temperature. And now we come to the influence of the octator structure. In dioctator 2-to-1 layer silicates, we have a so-called M1 position or a transposition. Octahedral groups are at opposite corners of the octahedron. And then we have 2 so-called M2 positions or cis positions. Those 2 positions share the hydroxide groups at a common edge. Yeah, and per formula unit, this is half a unit cell, you always need 3 octator positions. If the transposition is empty, those minerals are called transvacant. If one of the 2 cis positions is empty, then the minerals are called cisvacant. In the case of illites or micas, you can get the information on the octator structure from HKL reflections of the X-ray diffraction pattern. If you have not a textured sample, but if you have a nicely untextured sample, unoriented sample. Smectites, unfortunately, are topostratic disordered, so from X-ray diffraction analysis, HKL reflection would not tell you anything about the structure of the octator sheet. But luckily, Victor Tritz and some co-workers of him, they figured out from studying illites that there is a relation between the octator structure. In illites, we get the information from X-ray diffraction analysis and the dehydroxylation behavior. And they figured out that transvacant 2-to-1 layer silicates dehydroxylate at lower temperatures compared to the cisvacant dioctator 2-to-1 layer silicates. And so we now can use thermal analysis to obtain the information on the structure of the octator sheet of dioctator 2-to-1 layer silicates. And a PhD student of mine several years ago studied a huge set of samples of smectites, I think around 30 samples, and she found out that montmorillonites in most cases show a mixed structure of cisvacant and transvacant octator structures, followed by structures that are purely cisvacant, and only a few samples showed a transvacant structure of the octator sheet. And based on this, we were then able to create unambitious classification for the solid solution series of montmorillonite and bidylite. Montmorillonites, by definition, have the substitution only in the octator sheet, while bidylites by definition have their substitutions only in the tetrahedral sheet. But any natural sample will have substitutions in the tetrahedral sheet and the octahedral sheet. Yeah, and then we also have to remind ourselves that smectides are defined by layer charge between 0.2 and 0.6. Yeah, and then we created a system with systematic names that already give you the information on the structure, but we now have to face the fact that there is no monotonite, there is no bidylite, it's a solid solution series, and we have 96 structures. And if you also consider the interlayer cations, you have to multiply this by x. And those different structures have different properties. Yeah? Those different properties can be related to layer charge and cation exchange capacity, thermal stability, depending on the iron content or the structure of the octahedral sheet. Yeah, and also on direction if you apply moderated heat and you want to study the collapse of the interlayer. Yeah, it also is necessary to know about the contribution from the tetrahedral charge on the overall layer charge. Yeah, so please remember there is not such a thing like the montmorillonite or the bidylite. Yeah, there are many of those minerals around. Vermiculite, this is a sample of a trioctahedral vermiculite because dioctahedral vermiculite is only found in soils and then different to separate. So if you have vermiculite even at this large size I showed you at the beginning, then it's trioctahedral vermiculite. And therefore the dehydroxylation takes place at very high temperatures because we have magnesium in the octahedral sheet. But what is also important to know is that the dehydration of vermiculites takes place at higher temperatures compared to smectides because layer charge is higher, we have more interlayer cation, and the interlayer cation most of the time is magnesium with a very high hydration energy. Muscovite. Muscovite, dioctahedral mica, you would expect the dehydroxylation temperature below 700 degrees Celsius. But in muscovite we have the influence of the particle size, and a colleague provided me with size fractionated samples. And here you see how the particle size influences the peak temperature of the dehydroxylation. Again, this is a kinetic effect, yeah, because after the dehydroxylation, the water molecules have to find their way out of the material. Yeah, and if you have a large particle, the way is longer. And then dehydroxylation, or the peak maximum is at a different temperature. Yeah. Dehydroxylation of chlorides, even more complicated, because if you remember the structure of chlorides, you have the octahedral sheet in the interlayer, and you have the octahedral sheet of the 2-to-1 layer. And the dehydroxylation takes place in two steps. First, the dehydroxylation of this interlayer octahedral sheet takes place, and then this is followed by the dehydroxylation of the octahedral sheet in the 2-to-1 layer. And the ratio of three water molecules are evolved from the octahedral sheet in the interlayer, and one water molecule is evolved from the 2-to-1 layer. So therefore the ratio of mass loss is 3-to-1, but in some cases you will observe a ratio of the two dehydroxylation steps of the weight loss that is not equal to 3-to-1. And the reason for this is the oxidation of iron. If you have iron 2 in the chloride structure, which is very common, then the iron could be oxidized, and then hydrogen is evolved prior to the dehydroxylation. And then those hydrogen atoms are no longer available to form water molecules. Yeah, and this we could show for one chloride with a very high iron 2 concentration in the structure. There we were able to detect by mass spectrometer evolved hydrogen. And you see here that there's an additional peak that you cannot see in the evolved water. Yeah, because when you know about mass spectrometry, the gas molecules are ionized and are broken, so you have a so-called cracking pattern. So if you measure evolved water, you also will see the mass of 2 for hydrogen. Yeah, but if you then compare both curves, the curves of mass 2 and the curve of mass 18, and they don't have the same peaks, then this is the proof that yeah, we released hydrogen from the sample before the water molecules evolved from the sample. So, and now we come to the quantitative analysis. Sometimes thermal analysis could also be used for, I would say, semi-quantitative analysis. Quantitative analysis is not that easy, but it gives you a rough idea about the content of a certain phase, especially carbonates, and then if you compare those data with, for instance, Rietveld analysis, quantification of a complex sample, thermal analysis would give you, I would say, most of the time, maximum content. Yeah. And if thermal analysis tells you, okay, your sample contains maximum 10% of calcium carbonate, and your Rietveld analysis gives you 15%, then you have to think about the structures you used for Rietveld analysis and go back to your quantification by XRD. This is a mixture of, again, the kaolin with a high kaolinite content and calcite. Here you see the DSC curve. And you might think, okay, the dehydroxylation of the kaolinite and the decomposition of the calcite are well separated, and you might use the TG curve for quantitative analysis or for estimation of the content of both minerals. But what you see here, you don't see between the mass loss due to the dehydroxylation and the mass loss due to the decomposition of the calcite, you cannot determine a baseline. Yeah, you cannot see where one mass loss ends and where the next mass loss starts. And so you will have a certain error because you cannot put the boundary somewhere here. So yeah, and the reason for this uncertainty is that the dehydroxylation is still going on when the decomposition of the carbonate already started. Yeah. So you have a certain error. And we have a device that has a very nice addition that is called pulse TA. With a pulse TA device, you can add defined volumes of gases into your oven. And then this injected gas volume is also transported to the gas analyst, in our case the mass spectrometer, and then it can be used for the calibration of for instance, the signal of mass 44, which is characteristic for CO2. And then it's very simple mathematics. Here you see the CO2 evolved from our sample. Yeah, you can calculate the area of this peak. And then you can compare it to the peak area of this pulsed gas volume. Yeah? We know we can either inject 250 microliter or 1000 microliter of CO2. We know the temperature of this gas when we insert it in the device. From tables we know the density of CO2 at this temperature. Then we can calculate the mass from our pulses, and we can calculate the volume of CO2 evolved from our sample, we can transfer it into a mass, and then from stoichiometric calculation we can exactly determine how much calcium carbonate was in our sample. Yeah. There are other applications of pulse-TA. You also can use pulse-TA to study the interaction of a sample with a certain gas. Yeah, if you study catalyst reactions or whatever, yeah, you can use it in various ways. But we use pulse-TA for quantitative analysis, especially for carbonates. And I think with this I'm at the end before I show you some examples how to read a measurement or several curves of a measurement. So if you want to proceed with thermal analysis and you are interested in reading, so this book by Smykats-Kloss about these PA curves, there was a EMU school several years ago. There's a chapter about thermal analysis. And if you are interested in vermiculites, you should look for literature of the group of Graf von Reichenbach. He published quite a few papers on the hydration properties of vermiculites with different interlayer cations. Okay, and this slide gives you a strategy how to read the curves of thermal analysis. You search for the 4 characteristic thermal reactions of the clay minerals. You cannot really compare the curves I showed you today with your measurements. Sometimes it could work, yeah, but very often you really have to read your own curves or your own measurements. And what is also important, you always have to make sure that you get a consistent interpretation of all the measured parameters. Yeah, so if you see a mass loss, then the interpretation of your DSC curve should also be related to a reaction that involves a mass loss. This I will explain you with an example. And are there any questions so far before I'm going to explain you how to read the curve? Okay. On the left side, you see the 3 curves. Yeah, we have the DSC curve, we have the TG curve, and we have the mass spectrometer curve of evolved water. First, we have to identify the 4 thermal reactions of the clay minerals in the DSC curve. Dehydration, weak or strong. In this case, it's a weak dehydration peak, so this would indicate a non-swallowable clay mineral. Dehydroxylation seems to be a strong peak, but we don't know yet. Yeah, just from looking at the DSC curve, we don't really know if it's strong or weak. But here we see a strong exothermal peak for the recrystallization. This could indicate that we have a sample where we don't have substitutions. Yeah, we have a well-defined chemical composition, and therefore we see these strong, sharp exothermal reactions for the recrystallization of high temperature phases. Then we have a look at the TG curve. Here we said it's a weak reaction, and here we see there's hardly any mass loss, yeah, due to dehydration. Then we see a dehydroxylation. If you know that this is a pure clay mineral or nearly pure clay mineral, you remember I told you you should remember yourself the mass loss during the dehydroxylation of 1-to-1 layer silicates and 2-to-1 layer silicates. If the mass loss is larger than 5%, yeah, which we should remember for the 2-to-1 layer, or 4.85 for the 2-to-1 layer silicate, this indicates that here we see a measurement of a 1-to-1 layer silicate. Yeah. To make it even more correct, we first have to determine the dry weight. In the case of thermal analysis or TG curve, we always measure the moisture. Yeah, because the mass loss is always related to the starting weight, where we still have the water in the sample. And because of the measurement conditions that we apply, which means we always start our measurements with an isothermal segment at room temperature. This is necessary because when you open the oven, yeah, and put your sample in the oven, then you shut the oven. And if you would then start right with the dynamic heating, yeah, the oven atmosphere still needs to be equilibrated again by the flowing air. That's why we wait a little bit to get a good baseline for the mass spectrometer curves, and we start with an isothermal heating for 10 minutes. But if you think about smectites or clay minerals in general, very fine-grained, as soon as you start flushing the sample with dry air, you will remove the water molecules from the outer surface. Yeah? That's why we always have a so-called starting value. Yeah, because during this isothermal heating, we already lose some weight. And this we have to add to this first mass loss to determine the moisture. And this is what is explained here. You can have a look at it when you have more time after the conference. But here you see the difference between 100% and the starting value. This is the mass that we lost during the isothermal segment, plus the mass loss that you see here in the dynamic segment, gives you the moisture. Moisture can easily be transformed into the water content. You see there is very small difference at these low values, but if you think about the example with the 50% moisture, yeah, then you have a large difference between the moisture and the water content value. Okay, then we get the dry weight, so 100% minus the moisture. This is the dry weight. And then any following mass loss, we have to normalize to this dry weight, yeah? Because all the stoichiometric calculations we did are related to an anhydrous structure. Yeah, if you remember these calculations, even for the montmorillonite, there are no water molecules from hydration of the interlayer cations for these stoichiometric calculations. Anyway, as the moisture or water content are very low, if we normalize this mass loss, there's a small change from 99.6% to 10.11, but still it's way above or much higher than 4.85, so it must be a one-to-one layer silicate. The peak temperature is around 600 degrees Celsius. This indicates that we have a dirotator one-to-one layer silicate. And these are the informations we can retrieve from those measurements. If you don't have any further information, that's it. Yeah, then you need X-ray diffraction analysis to make sure that it's a kaolinite. But from only STA measurements, you only can say non-swallowable, one-to-one dirotator. But these are already many informations from my point of view. So this is a second example. Weak dehydration, non-swallowable clay mineral again. You find all the examples in the handouts. You don't have to take pictures, but then we have a look at the dehydroxylation again. This is now 4.6. We have to make sure that we normalize this 4.6. First, we have to calculate the dry weight, then we normalize it. It stays at 4.6. So this could be a 2-to-1 layer silicate. Yeah, and if we assume this should be a nearly pure clay mineral, we even can calculate the amount of this mineral. in December. I forgot to show you this with the first sample. Yeah, if we assume for the one-to-one layer silicate mass loss due to the dehydroxylation of 13.95 due to stoichiometry, this sample contains about 73% of kaolinite or non-swallowable one-to-one layer silicate dioptritor. And then we have about 27% of another mineral that shows no thermal reactions, or at least no decomposition reaction. Yeah, so we can have a rough estimation of the purity of if we want to separate clay minerals from a bulk clay. Okay. Dehydroxylation temperature is very high. So this indicates we have a triactital 2-to-1 layer silicate. Non-swallowable triactital 2-to-1 layer silicate. And content might be around 90–95%. Again, quite a few information we obtained from the thermal analysis. Another sample, this is more complicated. You might recognize this example. Is the dehydration weak or strong? It seems to be strong, but peak temperature is below 100 degrees Celsius, and this always indicates a non-swallowable clay mineral, but a very small particle size. Yeah, so you have a larger surface area that can be covered by water molecules. So again, we have a non-swallowable clay mineral. The dehydroxylation temperature is below 600 degrees Celsius or 700 degrees Celsius, so dioptritor. Again, a dioptritor clay mineral. But then now you see here that you have to consider the weight loss due to the dehydration to normalize all the weight losses that follow the dehydration. Starting value, difference to 100% plus the 4.1% loss during the dehydration result in the dry weight. Dry weight is then 94.27%. This dry weight we use to normalize the two other mass losses. This sample contains an impurity of 6% of kaolinite. We remember the mass loss of due to the dehydroxylation of kaolinite is close to 14%. If we have 6% of kaolinite, then mass loss of 0.84% is related to the dehydroxylation of kaolinite. So our normalized mass loss due to the dehydroxylation of 5.3 is higher than we would expect for a 2-to-1 layer silicate. But if we correct it by the impurity of kaolinite, we end up with 4.46%. And this again indicates that we have a 2-to-1 layer silicate in addition to the kaolinite. Yeah. And then we have another mass loss here, and there we have a trace of carbonate in the sample. You have to believe me because I don't show you the mass spectrometer curve of CO2, but exactly at this position we see evolved CO2 due to the decomposition of the carbonate. Yeah? And again, from a stoichiometric calculation, first we have to normalize this 1.2, which is I missed. So you have to do the normalization related to the dry weight, but then you can calculate the calcite content, and then you see it sums up to roughly 100%. 2-to-1 layer silicate diacritical, then the 6% of kaolinite, and then 3% of calcite. Yeah? If you end up with a sum that is much higher than 100%, you have to think about your interpretation. Yeah, but so this is really basic mathematics, and you can retrieve quite a lot of information if you carefully read your curves from the STA measurements. And you might remember in the dioxide 2 to 1 layer silicates, if the dehydroxylation takes place below 600 degrees Celsius, then it's a trans-vacant structure. If it takes place between 600 and 700 degrees Celsius, then it's a cis-vacant structure. Yeah? So we get quite a lot of information from these measurements. Another example, we still have a few minutes to go through some examples. This is now a mixture of two of the samples you just saw before. And here again, you see a feature that is really hard to read, yeah, because you don't know if these are two superimposing endothermal reactions or if there is an exothermal reaction involved. And to make this interpretation, you really need the additional information from the TG curve and from the mass spectrometer curves. Here you see the mass spectrometer curve again of evolved water. And you see you have two dehydroxylation reactions. Yeah? And in this case, we mixed the kaolinite sample with a talc sample. And here, the recrystallization of high temperature phases of the kaolinite superimposed with the endothermal dehydroxylation of the talc. So you only can put a number on the peak temperature of the exothermal recrystallization, but not on the dehydroxylation of the talc. Yeah? So this you only can do if you have a gas analysis attached or connected to your DSC-TG device. And again, step by step, we can go through all the steps. You read the intensity in the DSC curve of the dehydration and the dehydroxylation. Then you normalize the mass loss after you determine the dry rate. And then, yeah, you can retrieve the information that you have a mixture of dielectric 1-to-1 layer silicate and a trielectric 2-to-1 layers. This is an exercise to recognize the structure of dielectric smectides, either cis-vacant with dehydroxylation temperature between 600 and 700 degrees Celsius, and this smectide has a mixture of trans-vacant and cis-vacant octaedral sheets. This is a picture I wanted to show you of an artifact. If you have sodium in the interlayer of smectides, this can act as flux. And then your smectide starts to melt already during the dehydroxylation, forming spheres like you see here. And then some of the water that is evolved during the dehydroxylation is entrapped in these spheres. And with further heating, the pressure inside these spheres is increasing, and they kind of explode, they break. And then the water that was captured within these spheres evolves. And so for this material, you even find the interpretation in literature. This is a smectide from the Wyoming bentonite, that it contains some trielectric layers. Yeah, but this is an artifact. So that's why I always tell my students, if you don't perform the measurement yourself, please ask to get the samples back after thermal analysis was performed, because it took us also a while to find the solution of this small peak. When we had a look at the sample after thermal analysis, we saw the spheres. Yeah, they have a diameter of already 1 millimeter or 2 millimeters, so you can recognize them just by your eyes. Yeah, and if you have some peaks that you cannot explain at high temperatures, so it's always worth to have a look at the sample after thermal analysis was performed. And this is an exercise for the quantitative analysis by pulse TA. This is just simple calculation. And with this, we are just in time at the end of this lecture.